High-speed data networks, I mean, the absolute backbone of everything we do now, they have this mantra of zero tolerance for error.
Absolutely. Whether it's a gigabit data center or, a huge transoceanic link, the scale doesn't matter.
Data is moving literally at the speed of light, and if you lose just a fraction of a decibel of signal, the whole thing can just fall apart.
And it sounds like it's crazy complex science, but the foundation for validating these networks, it really just boils down to metrology.
The science of measurement.
Exactly. And today we're diving deep into Tier 1 certification, which is the fundamental proof that a fiber network actually works.
And Tier 1 really comes down to one tool,
Okay, go ahead.
an Optical Loss Test Set, or OLTS.
Right.
For you listening, think of the OLTS as a synchronized pair. You have a stable optical light source, the OLS at one end.
And a super sensitive optical power meter, the OPM, waiting at the other end to catch the light.
So our mission today is to really unpack the rituals, the procedures, everything you need to get this right.
That's it. We're going to confront the physics of measuring light, tackle the number one enemy of fiber, which is, shockingly simple, and then get into the absolutely critical steps for setting a true zero reference.
Okay, let's start at the end of the line then. How do we actually capture those tiny photons with the optical power meter and turn them into a number we can trust?
So the OPM's core function is, it's deceptively simple. It uses a photoelectric sensor to turn the light that arrives into an electrical current.
But the material that sensor's made of is everything, right?
It's everything. It has to match the wavelength. So if
Yeah.
you're working on older multi-mode systems, say at 850 nanometers, then a standard silicon detector is perfectly fine. It's efficient in that range.
But most of the critical data today is moving deeper in the infrared.
Yeah.
We're talking single-mode fiber at 1310 or 1550 nanometers.
And for that, silicon is useless. It just won't see it. You have to use detectors made of germanium or preferably indium gallium arsenide InGaAs.
And why is InGaAs the gold standard?
It comes down to two things. Superior responsivity, so it's better at converting light, but also a higher band gap.
Okay, why does that matter for the measurement?
A higher band gap means less electrical noise, less leakage when it's just sitting there. And that is absolutely crucial because the light arriving is so incredibly faint.
So you need to be able to tell the difference between a tiny signal and just the sensor's own background noise.
You got it.
Okay, that makes sense. Let's talk about the unit itself, the decibel, the dB. It trips up everyone coming from like an electrical background. Why this logarithmic scale?
Because the power drop over fiber is just massive. We're talking factors of thousands. A linear scale like milliwatts would be completely impractical. You'd have numbers with, tons of decimal places.
So the log scale simplifies it. And we have two different flavors, right? First is dBm.
Right, dBm is for absolute power. It tells you the raw intensity. 0 dBm is exactly 1 milliwatt.
Think of it as measuring the health of your light source or your receiver's sensitivity.
And then there's dB, which is for relative power. That's the one we really care about for certification. It measures the loss.
It's what the fiber itself stole from the signal on its journey.
Precisely. And to measure that accurately, the light source, the OLS, has to be just rock solid.
How stable are we talking?
We are talking microscopic tolerances. If your source fluctuates by even 0.1 dB, that's completely indistinguishable from 0.1 dB of actual fiber loss.
You could fail a good link.
Or pass a bad one. It happens more than you'd think. That's why a good OLS is specified to within plus or minus 0.05 dB over an 8-hour window.
And you have to let it warm up, right? That thermal stabilization period.
Oh, absolutely. 5 to 15 minutes minimum. You can't skip that. If you do, your reference will drift and your results will be wrong.
And we also have completely different kinds of light sources for multi-mode versus single mode.
We do. Single mode needs a powerful, narrow laser, like a DFB laser, to go the distance.
But for multi-mode, you're actually using an LED.
Yeah, because you need what's called an overfilled launch. The LED's broad, even light is perfect for filling that wider multi-mode core correctly for an accurate test.
Okay, before we get into the actual measurement, we have to talk about protecting the physics. Because the one thing that kills more fiber networks than anything else is dirt.
It is hands down the biggest threat, and it's all about the massive size disparity.
The core of a single-mode fiber is only about 9 microns.
Tiny, smaller than a skin cell, smaller than a particle of dust you can see floating in a sunbeam.
So when you make two dirty connectors, you're not just blocking light.
Oh no, you're compressing an obstacle the size of a boulder into a roadway narrower than a human hair.
And that causes, what you said, 4 catastrophic failures.
Yep. The first is obvious. The dirt absorbs and scatters light. That gives you high insertion loss and your link fails. Simple.
What was the second one? The reflection.
Exactly. Fresnel reflection. The dirt creates this air gap and impedance mismatch, and light reflects back towards the source, which can mess up your transceiver. That's return loss.
Okay, so block signal, bounce back signal. What about permanent damage?
That's number 3. If it's a hard particle, like a bit of silica, the force of mating the connectors can literally scratch or pit the glass.
And it's permanent. You just have to replace the connector.
It's done. But the fourth one is maybe the most interesting, especially in high-power systems like DWDM.
Right.
The optical power is so intense that it can hit a particle of dust or oil and fuse it. It literally burns it permanently into the glass surface.
Wow. Okay, so that's why the protocol has to be almost religious. Inspect, clean, inspect.
Every single time. With a video microscope before you ever made a connector, and the cleaning fluid you use is paramount.
People still use standard isopropyl alcohol, IPA. Why is that a risk?
2 reasons. 1, it's hygroscopic, so it sucks moisture right out of the air, which can leave a residue. But the bigger problem is static.
Electrostatic attraction,
Yeah.
ESA.
Yes. You wipe the ferrule, that friction creates a static charge, and that charge immediately pulls new dust right back onto the surface you just cleaned.
So you're in a vicious cycle.
Totally. That's why precision cleaning fluids are better. They evaporate faster, sure, but more importantly, they're engineered to dissipate that static charge.
And speaking of standards, the IEC updated its cleanliness spec back in 2022.
They did, and it was a really pragmatic, common sense change. The standard divides the connector end face into 4 zones.
The core, the cladding, and then the outer areas.
Right. And the revision basically said, stop failing connectors for cosmetic flaws way out on the adhesive ring where light never goes.
So it focuses all the scrutiny just on Zone A, the core, and Zone B, the cladding.
Exactly. And here's the most critical part. The new standard explicitly says that if a connector fails the visual inspection but then passes the optical loss test,
It's good to go.
it's good to go. Performance trumps a cosmetic flaw in a non-critical area.
All right, so our end faces are pristine. Now we get to the science of the measurement, which all starts with setting that zero reference.
Getting the baseline right? Yep. And the challenge is making sure your test set is only measuring the link you care about and not the loss of its own reference cables.
And just to remind everyone, you've already let your laser warm up for 10-15 minutes at this point.
Non-negotiable first step. Then you pick your reference method, and that choice has a huge impact on your accuracy.
So let's talk about the gold standard, the one that gives you the lowest uncertainty. That's the one-chord reference, method B.
That's the one. You take a single high-quality launch cable, connect it directly from the light source to the power meter, and then you hit the reference or 0 button.
The key being there are 0 mated connections in that reference setup.
0. That's the magic. Because when you then go to test your link, the final measurement includes the loss of the link itself plus the loss of those 2 connections at either end.
Which is what you actually want to know, right?
Yeah.
Especially in a data center where the connectors are the biggest source of loss, not the short fiber run.
It's the only true measurement. But you see people use the 2-chord method a lot in the field, sometimes because their connectors don't match.
And what's the risk there?
The risk is a false pass. With a 2-chord reference, you're including 1 mated connection in the zeroing step. You're basically telling the meter to ignore that first connection's loss.
So your final result looks better than it really is. It's optimistic.
Very optimistic. You could be hiding 0.1, maybe 0.15 dB of real loss. And on a tight budget, that's the difference between pass and fail.
You pass a link that's actually marginal, and then you get weird bit errors when you try to turn up the service.
It happens all the time. The 3-chord method is even worse, introducing the highest uncertainty. You really want to stick to the 1-chord method whenever possible for certification.
And there's one last sanity check, right, after you set the 0.
Reference verification. It's so simple, but so important. After you 0, you just mate your launch cable to your receive cable through a good adapter.
And that loss should be basically 0.
Or very close to it. Less than 0.1 dB for multi-mode, 0.2 for single mode. If it's high, you know your reference cables are bad before you even start testing the real link. Save so much time.
Okay, so we've nailed the reference, we've nailed the cleaning. What are some of the advanced tricks we need if things still look weird? Let's start with multi-mode.
Multi-mode is inherently a bit chaotic. Light takes all these different paths or modes down the fiber. Getting repeatable tests used to be a nightmare.
Which led to the legend of the mandrel wrap, right?
Yeah, yes. The old trick of wrapping your launch cable 5 times around a screwdriver handle or some specific sized rod.
To strip out the unstable higher-order modes, it always sounded a bit like voodoo.
It was necessary voodoo, but totally imprecise. I mean, you'd have two techs arguing in a data center because their meters were reading 40% differently on the same link.
So what's the modern scientific fix for that chaos?
It's called encircled flux, or EF compliance. It's an IEC standard that mandates exactly how the light power has to be distributed across the core as it's launched.
It's a template for the launch condition.
A very precise template. And the payoff is huge. EF-compliant gear reduces that measurement variation from, a crazy 40% down to a manageable 10% or less. It brings reliability to multimode.
Okay, let's pivot to single mode. There's a really cool diagnostic trick for finding macro bends, right? Those kite signal leaking bends.
Yeah, this is one of my favorites because you're using the physics of the glass itself to find the problem.
How does it work?
Silica fiber is just more sensitive to bending at longer wavelengths, so you can use that. You test the link at both 1310 nanometers and at 1550.
And then you compare the two loss results.
Yep. If the link is straight, the loss value should be pretty similar. But if you see a significantly higher loss at 1550, say a jump of more than 0.2 dB,
That's your bend.
that's your smoking gun. You have a pinch or a tight bend somewhere in that cable run.
Before we move on, what about the illusion of gain?
Yeah.
When your meter shows a negative loss number, a gainer, what does that mean?
It means your OLTS is crying for help. It's not real gain. It's a sign of a bad setup.
Almost always a bad reference, right?
Almost always. Either you used a poor two-chord reference or, more commonly, the light source wasn't thermally stable when you set the 0. It drifted, and now your baseline is completely off.
To wrap this all together then, let's clarify the roles of the two main tools. The OLTS we've been talking about, and the OTDR.
Right. They are often confused, but they do very different complementary jobs.
The OLTS is for Tier 1 certification. It's mandatory. Its job is to give you that one definitive number, the total end-to-end insertion loss.
It's the ultimate pass-fail. It tells you if the link meets its loss budget.
But if it fails, the OTS is just a black box. It says, nope, you failed, but it can't tell you where the problem is.
And that's where the OTDR comes in for Tier 2 testing. The OTDR is like a radar for fiber.
It sends a pulse of light and analyzes the reflections, the backscatter.
Exactly, and it uses that to create a visual map of the entire link, showing you the location and loss of every single splice, every connector, every fault.
So the OLTS tells you that you failed, and the OTDR tells you why and where. But why do we still need the OLTS for the final number? Why not just use the OTDR's total loss?
Because the OTDR's total loss measurement is inferred, not direct. It's a calculation based on backscatter, which can vary. The OLTS is a direct power measurement, power in versus power out. It's just inherently more accurate and repeatable.
So they really are complementary. OLTS for compliance, OTDR for troubleshooting and documentation.
That's the perfect summary. So to certify these incredibly fast networks, it all hinges on that rigorous protocol. Stabilize your gear, clean inspect every time, and use that one-chord reference method. That's how you get the definitive answer.
And if we look at the bigger picture, especially with emerging standards like 100G base IS-DIR in data centers, there's a fascinating shift happening in what network engineers are starting to worry about.
There is. Historically, it was all about insertion loss, how much light gets through. That was the only question.
But with these new super high-speed short-reach systems, the performance isn't really limited by power anymore.
It's not. The new limiting factor, the new thing that keeps engineers up at night, is a different metric entirely: reflectance.
How much light is bouncing back toward the source?
Exactly. High reflectance can destabilize the sensitive lasers in modern transceivers. So the focus is shifting from just how much light gets through to also include how cleanly the light gets through. To really future-proof a link today, you have to measure both loss and reflection.